When you're adding 0 plus 0, what's your answer? That's still a 0 in any number system. 0 plus 1. 1. 1 plus 0. 1 plus 0. 1. And 1 plus 1, that's 2. How do you write 2 in binary? 1 on the left, 0 on the right. Yes. So when you write that, the sum is really 0. And we have a curry equals to 1. The curry. Take it to the next location. It looks like a U, you know? Yep. It looks like a U there, but it's an A. A curry equals to 1, to the next bit. Now, if you were to add 4 bits, now, if you want a 4-bit adder, what you have to do is you have to go to the store. Well, they come at you on a strip of 4-bit adder. This is called a 1-bit adder. When you look at 1-bit adder, it looks like this. Usually has a digit here for a digit for B, we'll call it AN, BN, 1 digit. And you have a carry from the previous one, CN minus 1. It has a carry from the previous state. And now what you're going to have is the sum and the carry to the next state. That's what a 1-bit adder looks like. So what about if you want to buy a 4-bit adder, which they sell on the market, and you want to buy a 4-bit adder when you're adding numbers? Let me just give you an example mathematically how we add them. Let's say I have 0, 1, 0, 1. I want to add to it 1, 1, 0, 0. You start from the right. There is no carry the first one. The carry is 0. There's nothing. What's 1 and 0? 1. And no carry. What's 0, 0? 0 plus 0 is 0. What's 1 plus 1? That's a 2. That's a 0, carry 1. What's 1 plus 0 plus 1? 1 and a carry of 1. That's your carry here. On the last one, there's a carry of 1 coming out. So if you were to design a 4-bit adder, you want to design them, it will look something like this. I'm going to call these numbers AI, or yep, and this is BI. So for the first one, the carry coming in will be a 0. There is no carry for the first time you go to add. But now we have A0 and B0 here. That's the first column. That's this one. So you're going to have a sum of the 0 location, which is 2 to the 0. That's why it's called 0, the first one. Then there's a carry coming out of this. And the carry of this, now what you want to do with it, you're going to take that carry and move it up now to the next one. I'm trying to be neat, but it's not happening. Actually use graph paper. This is S1 and there's a carry again. Now this one is going to have A1 and B1. That will add these two digits, and the carry from that stage is coming to it. That's this column. So this is the 0 column, this is the 1 column, this is the 2, and that's the 3. Now the next bit, so this carry now comes up here, and we bring it down to the next state. And now I'm going to have two more inputs here, B2 and A2. That's this column here. It's going to give me a sum here of S2 and a carry coming out. And one more bit notice the last carry, there's no place to put it. That's a 4-bit adder. So eventually some of these numbers, when you add them, there's a carry coming out, and you can't just ignore it. And that's B3 and A3. And that's a 4-bit adder. You can buy this. They sell them. Each one of these is called a full adder. It's 1 bit. It's called a full adder. You'll need 4 of them to make a 4-bit adder. If you want to do 8 of them, you attach 8 of them the way you see that. And if your machine is a 12-bit machine, you can have 12-bit adder. They can add 12 at a time, or 16, you can add 16 at a time. The carry from each one goes to the next one, and so forth. So this is known as a 4-bit adder. If you were to buy it, you go, do you have any 4-bit adder? And that's what they give you. They'll give you a chip that has these 4 on it. It has A0, A1, B0, A1, B1, A2, B2, A3, B3. This will be grounded. There'll be 4 outputs here and 1 with a carry. And there's some power supply on them. I might have a picture. I don't know if we have a picture in our book for a 4-bit adder. Our book has pictures of different chips. When we go to the lab, you'll see some of these soon enough. A few weeks. Now I'm just looking at some of the pictures here. That's not one of them. These are AND, OR gates, NOR gates. 7474, nope. 7-segment LED, multiplexer, flip-flop. There's adders. Notice this is actually a 4-bit adder right here. Can everyone see it? First, for that chip to work, you have to make sure you actually attach this to 5 volts. You got to make sure you attach this to ground. That's the first thing you do. Now, you might be want to build an 8-bit adder. That's why CN, the carry in for the first one. Notice for this I made it a 0. If I'm doing a 4-bit adder, I'll make this ground. But what about if I want to attach another 4 next to it? So I don't want this one to be ground. So I'm going to take this one, attach that to the beginning of this one. If you were doing 8 of them, right? So that's why for this example, the first one is not a 0, because you might want to attach 2 of them and cascade there. But if you're starting with the first one, you ground that one, because the first digit you add, there is no carry to it. So this will be a 0. Notice if you're adding A1 to B1, you attach A1 here, B1 here, and there's the sum, that little sigma. That's S1. Then A2 and B2, you attach them, there's sum 2. I use 0 through 3, they're using 1, 2, 3, 4 here. A3 and B3, and there's a sum for 3. A4, B4, and there's the sum for 4, and that's the carry out coming out of that end. So that's a 4-bit adder you can buy already connected. So the only thing I have to attach is ground this, if that's the first one. If I want to make an 8-bit adder, I'll take 2 of these, and I attach this one for the first one to ground, and for the second one I'll take this piece here, C out, and attach it to the C in. I want this one to go to the next one, C input for the next one if it was an 8-bit adder. But you have to have power to these chips, otherwise they will not work. I gotta have 5 volts attached here and 0 volts attached right to 8. I don't think I have any of these in the lab. The number is 74283, and there's 7483 instead of 283. And learns the configuration a little bit different. It does the same thing. Look where my plus 5 volts, right here. Look where my C in and C out. Look where my ground is. So the pin number is a little bit different. So you have to know when you're looking at them, which one are you using? But it does the same thing. Does this one need a 5 volts to be on? Yes. Does it need a ground? Yes. But it's not pin 16 and pin number 8. This is pin number 5 and pin number 12. CN is pin number 13. CN is pin number 7 here. And maybe we can buy some of them, play with them. I don't have them. I know we don't have them in the lab. And again, when you go to the lab, you're looking at the chip, there'll be a bump on it like this, one side. If you're grabbing it, you always number them in a U shape, a U. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's always, you're looking at it from the top, that little U there, that little niche in it. Some of them have a dot on them right there. That says that's pin number 1 too. Instead of having that U there, they'll have a little hole there right to pin number 1. But when you count them, it's always a U-shaped count. So you know which one's which. All these have a U on them when you look at these chips. So the first one you're looking at on the left is 1 and go U-shape. This happens to be a 14 pin chip, 1 through 7, then 8 through 14. Okay.
How would you deal with multiple carries?
What do you mean multiple carries? You can't have more than...
Let's say it was,
because the carry from this goes right here. So you do 1 digit at a time. So you could, even if you had 1, 1, 1, want to do multiple carries? 1, 1, 0, 1, something like this.
yeah.
You go 1 and 1, 2, 0 carry 1. I don't know if that's what you meant. 1, 1, and 1. That's a 3, right?
Yeah.
3 is 1 carry 1. Number 3, it's 1 and 1. 1 and 2 is 3. 1 and 1 and 0, that's a 2. 0 carry 1. 1, 1 and 1 is a 3. 1 carry 1. So your number really, if you're looking at it, 1, 2, 4, 8, 16. Let's see what the value, that's the weight of each digit. Let's see if that answer is correct. This is the 1, this is the 2, this is the 4, this is the 8, this is the 16. 16 plus 8 is what? That's 26, isn't it 26? Let's see what you're adding. You're adding 1, 1, 1, 1, which is a 1, 1, 1, 1, that's a 15. The second number, 1, 1, 0, 1. 1, 2, and 8. What's 1, 2, and 8? 11. What's 11 plus 15? 26, and that's what this one gave me. That's what you meant by multiple carry?
Yes.
I wasn't sure like you meant on the design here. On the design, this will take care of it because the first one has a carry of 0, The 1 will comes right here now. This will give me a 1 with the carry 1, and that goes to the next one. So I'll take a couple examples like these just to make sure you got it. So let's add some numbers. We'll do the math first, and we'll do them using binary addition to see if they add up. I'll flip this. Let's say I want to add 5 plus 3. That's what? 8. Well, to write the 5, if you want to carry 3 digits, or if you want to use 4 bits, we got the 5 is 1. Remember the weight is 1, 2, 4, 8. The 5 is what? 4 plus 1. So it's 1, 0, 1, 0. That's what the 5 is. The 3 is what? 1 and 2. One plus 1 is 2. That's 0, carry 1. 1 plus 0 plus 1. That's a 2. 0, carry 1. 1 plus 1 plus 0. That's 2. 0, carry 1. 1 plus 0, which is 1. 1, 0, 0, 0. 1, 0, 0, 0. What's that equal to? That's an 8. Seven plus 9. 7 plus 9 is what? 16. We're going to have a little problem with that. 7 is 0, 1, 1, 1 if I'm using 4-bit. 9 is what? 8 and 1. So this is the 7, that's the 9. 1 and 1, 2. 0, carry 1. 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 So your sum, it looks like it's 0, but the carry tells you is what? It's 16. 0, 1, 2, 4, 8. The carry is which one? That's your 16. Is the answer 16? Yeah. 0, 0, 0, 0, and 1. That's a 16. Now, what about if you have negative numbers? Negative numbers. So sign numbers. Now we can go ahead and build a subtractor. But if you look at any of these computers, there is no subtractor. We use an adder to subtract for us. Somebody came up with this idea. They go, you know what? Let's do this. Let's come up with something where we use the first bit as a sign bit. Then the other bits, that's this bit here, and the rest of them as the number. And if you put a 0 on the sign bit, that will tell me the number is positive. And if you put a 1 in that location, that tells me the number is negative. If you're going to use 4 bits, I already killed 1 bit. So I'm in trouble. But if you wanted to write plus 5, there's the sign. Since that's a plus, it's a positive. So we put a 0 on the sign bit. That's your sign bit. Now the 5 is what? 4 and 1. If you want to put a negative 3, that's a negative number. Your sign bit will have a 1. Again, that's your sign bit. There's the negative. And the 3 is what? Isn't that 0, 1, 1? That's a 3. A lot of people don't like this idea because they eliminate one of those digits. So the biggest number you can have here is what? 7. Biggest number, 7. So that's not bad. I'm not a fan of it. I don't want to use a sign bit like this. And just if it's 0, you know. So what about if you have to write 8 here, plus 8? You can't. Or 9. You can't. Because once you write 8 or 9, that digit becomes what? 1. So how would you write plus 8? If you have 4 bits, we know what 8 is. Is what? It's 1, 0, 0, 0. That's what 8 is. But people are going to see the 1 here, they're going to think that's what? That's a negative, negative what? Negative 0. Because if that location is a sign bit, if it's 1 in it, that's negative number. If it's 0, that's a positive. So that limits your how big the number you can put there with 4 bits. So you have to go to 5 bits to be able to get the 8 there and the 9 there. So losing that bit was an issue. Like, I don't want to lose it. So some people came up with a different idea, and that's called a complement. They said, let's do this. Let's use the complement. And actually, we're using something called 2's complement. For negative numbers. And there's an equation to calculate the number. So for example, if you want to write, let's say I'm using 4 bits, and I want to write negative 4. They say, well, if you're using 4 bits, you're going to write the negative 4 as 2 to the power of 4 minus the 1. 2 to the power of 4 minus 1, and minus 1 minus the number. If I'm using 4 bits. And you got to do some math, and people say, I don't like the math there. I got to do some math here. Somebody else came up with a brilliant idea. So you want to write negative 4? They go, yes. He said, don't pay attention to the sign. Write the 4 in binary. What is 4 in 4 bits? 0, 1, 0, 0. Isn't that what 4 is? 1, 2, 4, 8. Now change all the 1s to 0s, all the 0s to 1s. Flip them. 1, 0, 1, 1. That's known as 1's complement. Then come back and add 1 to it. Actually, that's 2 to the 4. not minus 1. I'm using 4 digits, not a minus 1 there. So now let's add 1. What's 1 and 1? 0 carry 1. What's 1 and 1? 0 carry 1, 1, 1. Two to the 4, 16 minus, I think it's the number. What's the equation? I don't use the equation, so I forgot even the equation. Minus n, I think. That's 12. Yep, that's how we do it, because everyone does it this way. I think it's 2 to the n minus n. Where is it? I don't even know if the equation's in the book, but I think it's 2 to the n minus the number itself. It might be minus 2 to the number of digits minus the number, which is like the absolute value of that number minus the 4. So 2 to the 4, which is 16. 16 minus 4, which is what? 12. Yep. But nobody will use that equation. We use the 1's complement, add 1 to the 1's complement, and that'll give you the 2's complement. What you get in there is called the 2's complement. So we're going to write the negative 4 as 1, 1, 0, 0. You'll see in a few minutes the advantage. The advantage of that, instead of using an adder and subtractor in your device, the adder can do addition and subtractions. The same device can do both, and will give you the right answer.
Isn't that just 4 with a sign bit for negative?
Well, it looks like it. Yep. Take negative 9. 9 is what? 1, 0, 0, 1. That's the 9. Do the 1's complement, which is what? 0, 1, 1, 0. That's the 1's complement. Of 9. So this is the number 9. This is the 1's complement of it. Add 1 to that. Be 1, 1, 1, 0. And that's your 2's complement. So notice that's the 2's complement of negative 9. We do the 1's complement, add 1 to it.
We don't have the regular, right? It's only the 1's complement.
Yeah, just we do the 1's complement. Just like there's a math equation that will give you that number without having to go through these steps. But that's what everyone does. They do the 1's complement first, add 1 to it. That's your 2's complement.
So I was looking at the top where the 9 was also. Yeah.
2 to the 4, which is 16. Yeah, there's an equation. There's a minus 1 in the equation. I just don't remember off the top of my head with that equation.
It works with
Which one?
4 minus 9
Minus 1?
minus 9 equals,
2 to the 4 minus 9
yeah,
equals that number. Did it work?
yeah.
Yep. Whatever that equation, you know. This number is 7 here.
Yep, 2 to the 4, 16.
16 minus 9, which is, it is 7, yep. So it is actually, take a negative number, you go 2 to the number of digits. N is number of digits. Minus n, which is big N, is the number actually. But nobody does that equation. Nobody really uses that. We just use the 1's complement, add 1, there's your answer.
For the last one,
Yes.
is it 1 plus 1 equals 2?
Where's 1? No, that's that number. We're looking at this. Right? This is just the 9 here. And this is the 1's complement. So once I'm here, that's the 1's complement of that number. Now you add 1 to this answer, not the top one. You're not adding all 3. You're adding 1 to the 1's complement to get the 2's complement.
That's why it's not two.
Yep. Same thing. This is the 4 here. This is 4. Take the 1's complement of that, which is this. Now add 1 to this answer. That's why it's 0. 1, 1, 0, carry 1. 1 and 1, 0, carry 1. That's 1 and 1. So if I want to add, for example, or let's say I want to add, let me take an example. I'll do one more because I think you're still shaking on that. Let's take a negative 5. Let's take the 5 and write that as binary. 5 as binary is what? 0, 1, 0, 1. Now I'll leave a space. Do the 1's complement. 1's complement, you turn the 1's to 0, 0's to 1. 1, 0, 1, 0. Now add 1 to this. I left a space between them just to see. I'm done with that. I'm right here. Add 1 to the answer here. To this answer. What's 0, 1? 1, 1, 0, 1. This is the 2's complement. (16) minus the 5 is what? 11, 8, 2, and 1. That's 11. How about a minus 1? Let's find out what the 1 is in binary. The 1 in binary with 4 digits is 0, 0, 0, 1. 1's complement. 1, 1, 1, 0. Add 1. What's 1 and 1? I mean 0 and 1. 1, 1, 1, 1. That's the 2's complement. What is 16 minus 1? 15. Is that a 15? 1, 1, 1, 1. That's a 15. What about a negative 0? I'm just having fun. What's a 0? 0 in binary is what? 0, 0, 0, 0. 1's complement. 1, 1, 1, 1. Add 1. 1 and 1, 0, carry 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 1. So if you're looking at 4 digits, you go, the complement of negative 0 is 0. There is no negative 0. 0 is 0 with the carry of 1. Now, when we add, you're going to see that when we start doing addition with the complement, the carry out here, we ignore that carry out. We don't count that. Any carry out, we're going to ignore it. And you'll see the math in a minute. Because if you leave that one, it goes, oh, that's a 16. Well, negative 0, there is no such thing as 16. Negative 0 is the same as plus 0, which should be 0. So that carry out here, we're going to neglect that. So let's take an example and show you how that works with 2's complement. I'll do a few examples. Let's try negative 5, and I want to add to it 7. Mathematically, what's the answer? Plus 2. Okay, let's see. I'm almost done, just give me a few minutes. Let's write the negative 5. Well, before I do anything, let me find what the binary number for 5. For 5 is what? 0, 1, 0, 1. What do we do next? We add 1 to the, we complement that to get the 1's complement, which is 1, 0, 1, 0. Add 1 to it, and what are we going to have? 1, 1, 0, 1. That's what negative 5 and 2 is complement. 1, 0, 1, 1. That's a negative 5. Let's look at plus 7. 7. 7 is what? 0, 1, 1, 1. Let's add them now. My answer should be plus 2. Let's see if we get plus 2. 1 and 1. 0 carry 1. 1, 1, and 1. That's a 3. 3 is what? 1 carry 1. 1, 0, 1. That's a 2. 0 carry 1. 1, 1, and 0. That's a 2. 0 carry 1. Remember I just said ignore the carry out in addition and complement. When you ignore that carry, what's your answer? 2. Positive 2. Let me try another one. Let's see. Since I have the negative 5 handy, maybe I'll use it. What's a negative 5 plus 6? We know the math says what? 1 plus 1. The negative 5, I just did that. That's the 2's complement of negative 5. So that's 1, 0, 1, 1. The 6 is what? Is that 4 and 2? So I took advantage of this because I know the answer is negative 5. I cheated. I put it there. So I've done the complement already for it. What's 1 and 0? 1, 1 and 1. 0 carry 1, 1 and 1, 0 carry 1, 1 and 1, 0 carry 1. Ignore the carry. What's your answer? 1. Take advantage of that negative 5 since I did it. Now when you add these, what should we have? Negative 3. Okay, let's see. We know what the negative 5 is. I just did that twice, right here. The 1's complement of that, or the 2's complement, is this one. What's a plus 2? Plus 2 is what? 0, 1, 0, 0. Let's add them. 1 and 0. 1, 1 and 1, 0 carry 1, 1 and 0, 1 and 1. That doesn't look like negative 3. Take the 2's complement of this. If you take the 2's complement of that, do the 1's complement. The 1's complement, flip the zeros to 1's. So 0, 0, 1, 0. Add 1 to that. 1, 1, 0, 0. What's that number? Isn't that 3? So the answer should be negative 3. Is that what the answer is? Now here's what you have to remember. When you're adding 4 bits together, you're going to have an overflow anytime if you're adding the same sign. If you're adding the same sign, you will have an overflow. Like, for example, 7 and 8. 7 and 8 is what? 15. You're okay there. 8 and 9. What's 8 and 9? Is that more than 15? You have an overflow. Or negative numbers. What's negative 10 and negative 7? Negative 17. Overflow. So overflow occurs when the sum is out of range. For 4-bit numbers, the range is between negative 8. The sum has to be between negative 8 and plus or equal to 7. Negative 8 or 7. Now, how did I know to do the complement? Why they're saying 7? Because they still looked at that digit. That's 1. That's a flag, because 7, that tells me that's a negative number. So that's why I did the complement for that. So you will have an overflow anytime your sum is for 4 bits. Anytime your number is bigger, the sum, the answer is bigger than negative 8 and less than or equal to 7. You have an overflow. So if you add 5 and 4, what's that number? 9. Is that bigger than 7? You're going to be wrong. 4 bits is not going to do it. So when you do your math, it looks like you got a negative number here, because the 1 here, you do the complement, you go, oh, that's a 9. It's not. I mean, the sum is 9, but it looks like a negative 7. Because you do the complement of that, becomes 0, 1, 1, 0. Add 1 to it, 0, 0, 1, 1, 1, which is negative 7.
So why do we need it for negative 3? Complement.
Well, if you look at your number is a negative number, not because of the range.
Oh.
And to get the number back to the original value, we do the 2's complement. Remember, negative numbers are written in 2's complement.
Okay.
So if your answer is going to be a negative number, it's going to be written in 2's complement.
Okay.
So you have to do the 2's complement to get the original number back.
Thank you.
You're welcome. It says here, indeed, whenever we add 2 positive numbers, each beginning with 0, and get the result that looks like a negative number, means begins with 1, there is an overflow. Again, when you're adding 2 negative numbers, each one begins with 1, and obtaining a sum that's more negative than negative 8, the product will have an overflow. So there's limitation. Notice negative 5 and negative 4, that's a negative 9. You outside the range, it will not work here. You're going to have an overflow. That looks positive. Notice when you're adding a negative and negative, look at your number, it looks positive. How can you add 2 negative numbers that begins with 1, end up with a positive result? Again, the way the machine is programmed, we look at them, if that number looks like a 1 here, it's like, uh-oh, that looks like a negative number. How do you fix a negative number? You take the 2's complement of it. If that digit is 0, it's positive number, you're fine. If you're adding 2 positive number, getting something that looks negative, which has a 1 here, you have an overflow. If you're adding 2 positive numbers beginning with 0, and your answer looks like has a 1 in it, that's a negative number, you have an overflow. So there's if you go to 8 bits here, your number can be bigger, but it's still going to be limited. I mean, the reason we get the limit to be between negative 8 and positive 7. Why? Negative 8 is 2 to the power of 3. That's what negative 8. And the 7 is what? 2 to the power of 3 minus 1. That's where the 7 came in, because using 4 bits. Now, if you're using 8 bits, you still have limitation. For 8 bits, it's going to be from negative 2 to the 7 to 2 to the 7 minus 1. What's 2 to the 7?
256.
Is it 256? 2 to the 8, I think, is 256. 128 maybe? 120. So from negative 128, if your sum is between these numbers, and 127, you'll be fine. If it goes outside that, you'll have an overflow. If you're using 16 bits, your sum has to be between negative 2 to the 15 to positive 2 to the 15 minus 1. If you're using 32-bit machine, 2 to the 31 negative and less than 2 to the 31 minus 1. The advantage why we like that, I don't know if our book has a picture of that, sometimes we do, because you can use, I didn't see it in our book, you can use the same design, the same memory chip here to do addition, subtractions by adding a couple of gates to it. Too bad our book doesn't have it, but I'll get you that picture next time because we passed, way past the deadline for the class. Okay, homework.